So welcome back to Calculus 1, and what we're going to take a look at right now is what is calculus. So one idea about calculus, kind of a general idea, it's a study of infinity. And I'll show a few examples of how it's a study of infinity. So the idea of infinity, it's a single word that means a lot of different things in mathematics. So one idea about infinity is if you just think about a number line, infinity just means go right forever. When I use these counting numbers here, which is kind of where like a basis of mathematics, the counting numbers go on forever. There is no largest counting number. If you say, hey, a million's the biggest counting number, I say, well, 1,000,001 is bigger, right? So we can always get a bigger counting number. Eventually we run out of names for them, but we can write them down. Sometimes we use things like scientific notation to talk about really big numbers. Now, infinity, however, is more than just going to the right forever on a number line. That's just one version of it. If I zoom in on 0 to 1 there, so let's put 0 over there and 1 over here, there are a lot of fractions in here, right? Like 1/2 is right in the middle. And right in between 0 and 1/2 is another one, like 1/4 is over there. And in between 0 and 1/4, right, is 1/8. So there are infinitely many fractions between 0 and 1. So infinity is a weird idea because it's got a lot of different interpretations and meanings. So there are infinitely many counting numbers. Between any two counting numbers, there are infinitely many fractions. And if we zoom in on any pair of fractions, like if I zoom in on that 1/8 to 1/4 on a number line, we're going to find that there's infinitely many fractions in there too. And every time we zoom in on a pair of fractions, we're going to find again that there's infinitely many fractions in between there. So infinity is just weird, but it is the basis of calculus. This idea that we can break things up into little tiny pieces forever and ever and ever, or we can go in some direction forever. And so these are two versions of infinity that you've come across in your mathematical life, and we're going to take advantage of them to do what we call calculus. Another example of infinity that you see regularly but don't really think about would be a particular fraction I didn't show, but it would be somewhere over here-ish, the fraction 1/3. Okay? A lot of people prefer decimals over fractions, and decimal for 1/2 and 1/4 are pretty straightforward. Right? So 1/4 is just 0.25. But when we try to deal with 1/3, which lives over here somewhere on this number line, 1/3 as a decimal is a little weird, right? It's these repeating threes forever and ever and ever. So we have this particular place on a number line. We have 1/3 of something, like, right, I can cut a candy bar into thirds, or a cookie into thirds, or a pizza into thirds. And so the idea of 1/3 of something is pretty simple and straightforward. But then all of a sudden we try to switch to this idea of decimals, which most people like better than fractions because they're easier to work with. And we get this infinitely long decimal. What the heck is up with that? So just a little more about 1/3. Which we say is 0.333 dot, dot, dot. These three dots are called an ellipsis, which means continue what you see here. Sometimes we write it with a bar over the top to mean continue that 3 forever, right? And that forever thing is kind of weird. When I read a decimal, often we say 0.333, which is slang for the decimal. These each have a place value. So that right there is 3/10. And the next one would be 3/100 is the proper way to read it. And the next one is 3/1000. And that pattern just keeps going, right? Where I put another power of 10 in the bottom here. Every one of them has a 3 in it. So I could factor that 3 out, and then I get 1/10 plus 100th plus 1,000th. And that goes on forever and ever and ever. Again, we could view that decimal wise, so just a little play with math here. And one important thing you got to know about math is it's not just a set of rules, it's an exploration. You got to kind of play around with it to figure things out. So this pattern just keeps going on and on forever. And think about this for a second. If this goes on and on forever and it's 3 times something and it equals to 1/3, then over here, this would have to be 3 times what? What does all of this stuff add up to? If 3 times it has to be 1/3. Any thoughts on that? One. Nope, it doesn't add up to 1, because then 1 times 3 would be 3, but I need it to equal 1/3. Right? This has to equal 1/3. All I did is factor the 3 out. So 3 times what is 1/3? 0.1. No, 0.1 is the first part. That's a good guess too, right? So there's my 0.1, but then I have plus all this other stuff. So it's got to be bigger than 0.1. Other guesses? All right, nobody yet. So just, there's a couple ways to think about it. One way would be to say, okay, this is 1/3. I'm multiplying something by 3 to get 1/3. So that means it's got to be 3 over something. And so the question is 3 over what reduces to 1/3? Well, if you were to go over to this side and multiply top and bottom by 3, you would see that this bottom number had to be 9. So this would be 3/9. So 3/9 is 0.333. And if I factor out the 3, I get 3 times 1/9. And so that means 1/9 has to be 0.111, repeating forever. Some other weird things that happen with infinity. Check this out. We believe that 1/3 is equal to 0.333, repeating forever. We believe that that's not 1/3, let's do 2/3. We believe that 2/3 is what? 0.666, repeating forever, right? And if we add these guys together, well, 1/3 plus 2/3 is 3/3. And 3/3 is really 1, but on the other side, if I add decimals, right, I add corresponding place values, right, even with the 0 there. So 0 plus 0 is 0, 3/10 plus 6/10 is 9/10, 300 plus 600 is 900, 3,000 plus 6,000 is 9,000. I'm going to get 0.999 forever and ever and ever. And if that does go on forever, then 0.999 forever is exactly equal to 1. These two are the same number. Kind of weird, huh? I think everybody accepts that that is true, and everybody accepts that that is true right there. And if these two things are true, then that has to be true too. So I'll let you think about that some more. All right, so again, calculus is the idea of studying infinity in different ways. you might think that that's kind of like an overly simple example of infinity, but that's some pretty deep, subtle stuff that's going on here. This gets studied further in Calculus 3. So what about Calculus 1 and Calculus 2? So calculus has several different versions of it that study infinity. Usually the first one that's studied is called differential calculus. And the idea of differential calculus is looking at rates of change. And so we'll take a look at a few examples of rates of change. So one of the simplest examples of rates of change would be like the speed of a car. Velocity. So that's one example of a rate of change, and we'll look at a lot of different rates of change, like populations change over time. And the other part of calculus, so this is calculus 1 up here. Calculus 2 is a different study that's called integral calculus. And integral calculus studies areas. So for example, with integral calculus, we might have some graph, like maybe a parabola. So maybe this is the graph y equals x squared. And I might want to know from this point here at the origin over to this point over here, what is the area underneath there? And what makes that challenging is that curved surface right there. Like I know the formula for the area of a rectangle, I know the formula for an area of a triangle, I know the formula for an area of a square and a circle, but what if I throw some other curve at us, like a parabola, or perhaps like a sine or a cosine wave? So this might be the graph, the sine of x. Can I figure out how much area is underneath that curve? That arc right there is not a part of a circle. It's not a circular arc, it's a special arc. It differs from a circle as a parabola is different from a circle. Even though the sine is related to a circle, that is not a section of a circle. And the interesting thing about rates of change in areas, it turns out that they are related to each other. So rates of change are things like, for velocity, that would be change in distance over change in time. And often we abbreviate that change in distance over change in time. And so in a previous course, like college algebra, you may have seen something like this triangle right here with a D next to it, and maybe that triangle with a T for time. The D here would be like my Y value. So that would be, this is the Greek symbol delta, by the way, delta Y over delta X. So again, that symbol right there is capital Greek delta. And it stands for change. Okay, so anytime you see that symbol, it means, hey, we have a change. Change in distance, change in Y, change in time, change in X. So differential calculus is related to this division here between these changes. Integral calculus comes from an area, and the simplest idea of an area is maybe a rectangle. So I could take a small chunk of this area down here and turn it into a rectangle. And that rectangle right there has some a width here, this little tiny width at the bottom. Width, there we go. And that distance there, I could say, is a change in an x value. So I'm going to call that delta x. And then over here on the side, the height of that rectangle is a y value. So the area of that rectangle right there would be the width delta x, that's chunk of an x value, times the y value. So here what I'm trying to get at is this idea of area, which is a multiplication, and this idea of a rate of change, which is a division, they are related to us. Notice the delta x here and the delta x there. So by the end of this course and the beginning of the next one, we'll get into the real how are these two related. And I'm going to show that today, kind of jumping way ahead, and then we'll back up and learn more about what these differential calculus things are. So let's take a look at an example. So what we're going to do here is we'll take a look at speed. And let's suppose that the velocity of a car is 60 miles per hour for a little bit, which I could write as a fraction, 60 miles over 1 hour. So we just see this car driving down the highway, it's moving 60 miles per hour, and we watch it for a few seconds. Okay. So I can make a graph of this situation in a couple of different ways. So one way would be to just think about the velocity over time. So this axis can be my velocity, and this axis can be my time right here. And let's suppose we watch it for 1, 2, 3 seconds. Or let's make it hours, because we have velocity in hours. So we observe this car moving, we watch it go for 3 hours, it's moving 60 miles per hour. So let's just say 60 is going to be up here. 1, 2, 3, 4, 5, 6 per. So that's my 60 miles per hour. So we have a constant speed here. So when we first observe the car, it's moving 60 miles per hour. 1 hour later, it's still moving 60 miles per hour. 2 hours later, it's still moving 60 miles per hour. And 3 hours later, it's still moving 60 miles per hour. And so we get this flat graph here, right? V equals 60. The other thing we can think about here is position, right? So the car is moving from when we first saw it. An hour later, it's 60 miles further away. So this is a graph of velocity here. Let's take a look at a graph of position and see how it's related. So on this graph, we'll have D for distance, and distance will be miles here. And we'll have T for time here, and time is going to be hours again. And let's see, I'm going to scale this one a little bit different. Let's put, how about 60 miles is going to go right there. And then this will be 1 hour right there. So at first, the car is right where we first saw it. So that's position 0. And then 1 hour later, it's gone 60 miles because it's moving 60 miles per hour. Okay. 2 hours later, how far has it gone? Anybody? 120 miles, yeah. So if from here to here is 60, then another 60 is right here at 120. And so 2 hours later, it's at 120 right there. So in this case, and let's might as well do 3 for fun here. 3 hours later, it's gone another 60, which should put us at what, 180? Doing good addition today. And so that's going to be this point right here. So we get this nice straight line, but this one isn't horizontal, it's at an angle. Okay. Well, what slope is this right here? Well, we can see here in the graph that from this point to this point, we went up 60 and then right 1. So the slope here is 60 over 1, which is, right, my velocity right there. So the distance is equal to 60 times the time. So a couple things to think about here. Again, this graph over here is velocity. That 60 right there is miles per hour. This 60 over here is just miles. So if I take the velocity graph and I think about this for a minute, well, I believe that distance equals rate times time. So that's a common formula we've looked at. Distance equals rate times time. And my rate here is my velocity up there. So I had that d equals 60 t. So we're taking this 60. What is that 60? That is the 60 miles per hour. So for example, at 1 hour later, my distance formula says to take 60 miles per hour, let's put the units in there, and multiply that by the time that's gone by, which is 1 hour. And the cool thing about putting the units in there is I can clearly see that the hours are going to cancel numerator versus denominator. No more hours here, leaving just an answer of 60 miles. All right, so this multiplication converts, because of the slope, miles per hour into miles by multiplying the hours out. How does that relate to this graph over here? Well, from here to here is my 1 hour. From here to here is my 60 miles per hour. And I multiplied that 60 miles per hour, that vertical representation of the speed, by this horizontal representation of time. And so what that multiplication does on this graph is it gives me the area of that rectangle. So the area of that rectangle leads to that point right there. So what we did was we used velocity graph and a multiplication, which can be interpreted as an area, and that area turned into a point over here. If I continue on to 2 hours, and I take 2 times 60, that gives me this whole area over here. 2 times 60 is 120, which gives me that point over here. So when I make the transition from the velocity graph to the distance graph here, this transition takes a rate and an area and gives us position. This idea in this direction here is what we call integration. And that's the calculus 2 idea. Calculus 1 takes things the other way around. It takes this distance graph here and looks at the relationship between these points here. How do I get from this point to that point? Well, I would rise 60 miles and I would run 1 hour. So I get a slope m of 60 over 1. And again, that's 60 miles over 1 hour. So I take the graph of distance and time, and I find the rate of change. And I can see that the rate of change, missing a letter, there we go, is 60, which is this 60 right here on the horizontal line. So taking the distance versus time graph and changing it into a velocity graph, that's what we call derivatives or differentiation. So this is just a simple example of how calculus 1 and calculus 2 are related to each other. The idea that speed can be turned into distance and distance and time can be turned into speed are calculus 1 and calculus 2 ideas. Now here I used like the simplest possible example, right? I started with a horizontal line, a constant, right? Like y equals 60, and I turned it into y equals 60x. And these are the simplest kinds of functions that we can work with. It gets a little more complicated when we start with curves that aren't as simple. So let's move on to a slightly more complicated example. New page. Let's see, I'm going to scale these a little bit differently. So for now, I'm just going to call these y and x for a minute. Oops, x, there we go. And we'll get a little more complicated than the last one in that we'll start at 0, 0, but instead of being a horizontal line, we're going to start with a sloped line. So this y is going to be my velocity. And the x is going to be my time. And just for fun, let's mix things up. Let's let time be in seconds this time, and velocity be in feet per second. So let's say we start off with no velocity, and then 1 second later, our velocity is 1. 2 seconds later, we'll let our velocity be 2, and 3 seconds later, we'll let our velocity be 3. So I get this slanted line to start with. And what I'd like to do is I'd like to turn this into a graph of position. And so we'll do the same scale, but it's going same numbers, but they're going to have different values or different interpretations. We'll do the 2, 4, 6, 8, 10 here, 1, 2, and 3. So this is going to be my position graph this time. And that's going to be in feet. And this is going to be still time, and that's going to be in seconds again. So I want to try and find a relationship between, instead of a constant velocity here, start off not moving, and then after 1 second, we're going 1 feet per second, then 2 feet per second, then 3 feet per second. So we're speeding up here, is what this graph shows. And I'm going to make this just a little bit easier just for fun, and we can clean it up later. I'm going to turn this into steps. So let's say I was going 1 foot per second for the whole first second. And for the whole second, I'm going 2 feet per second, and then 3 feet per second for the next one. So if you then think about position is going to be equal to velocity times time. Well, my velocity is 1 here for 1 second, and so the area here is 1. So after 1 second, I'm going to have a position of 1. What's going to happen if I simplify this to 2 seconds? Right, so this is going to be 1 by 2. 1 plus 2 is going to be 3, right? If I add all this area up to there. So at 2, I jump up to 3 here. And then if we jump over here and get this further position, so this rectangle shows I've gone 1 foot in 1 second. This one shows that in the next second, I went 2 feet, because this rectangle right here is 1 by 2. And this next one right here is 1 by 3. So that's going to have an area of 3. So I have an area of, let's write this in here, area 1, area 2, area of 3. So 1 plus 2 plus 3 gives me 6. So my next position point over here is going to be 6. And what I want you to notice here is that these points don't line up, right? So to get from here to here is different slope than getting from here to here, right? Because I'm speeding up according to this over here. Any guesses as to what kind of graph I might be building here with these line segments? A parabola, excellent guess, Cole. Yeah, so we are roughing out a parabola here based on that line. This position graph here, the slope of each line segment is the speed of the object. So this graph for position shows both position and the slopes show speed. This graph over here shows speed, and if we draw some areas in, we get position from the areas. So again, this direction is integration. looking at a graph like this to try and find the slope, that's speed. So if this was actually a parabola, ooh, it's stopping time. One more quick note on this, then I'll shut up and tell you what's next. So if this was actually a parabola, the problem with a parabola is if at this position point right here, so again, if this was position versus time and my graph was a parabola, how do I find the slope here? If I have 2 points, I can easily find the slope, right? I give you this point, I give you that point, you have a slope formula to find that slope right there. But how do you find the slope at a single point? Okay, that's where things get trickier, and we're gonna have to throw some infinity into the mix. And I'll talk more about that infinity tomorrow. So because of the intro to the course, I only got through about half of what I wanted to get through today, but that's okay. We will catch up on that tomorrow. So what I need you to do is check out the textbook if you haven't already, read through the syllabus, do the intro to mom assignment, and then start reading this other version of the book here. And what I've covered so far in here is this intro section that talks about how velocity and position are related. They show a little speedometer, odometer from a car. And example of a constant velocity and how position changes. And we kind of did an example, like we did half of this example right here. So we're halfway through this section 1.1 in the old book. And so by tomorrow, I'll have covered most of this. This is just a review of functions. And there's some stuff in here we're not going to talk about that I'll mention tomorrow. But over today and tomorrow, we'll cover section 1.1 in here, section 1.2. We kind of did that one here today, and section 1.3. And section 1.3, there it is. Yeah, so we'll get to this one tomorrow. And this right here, the velocity at an instant in 1.2, that's closer to what's in section 2.1 in our real book. So we'll transition from here to the real book tomorrow. So again, your goal is to look at the introductory stuff and start taking a look at the section 2.0. If you have time after you get that stuff done to start poking around in the first homework section, then please do. But it's a really good idea to read the book before you do the homework. So try reading through the beginning of this right here, and then we will move on tomorrow.